Yeah. So what did we get here? By expressing the base, if the base is a perfect power, right? So that is the key thing here. So if the base is not a perfect power, then there is no point getting into this kind of a corner case. But if the base is a perfect power, then you could do the power swapping technique, taking it one more level down. And so by doing the power swapping technique of 2 to the power 4 to the power 3 to the power 17, we have got a new non-distinct base which we have found, which is 16 to the power 51. Actually, 8 to the power 68 leads not only to a non-distinct of 64 power 34, but also to 16 power 51. So I think this covers the corner case also. So now if we just go back, our key idea is we don't want to compute in a brute force way all the values, because it is memory inefficient. So by taking the table notation which we came up with initially, we come up with a different kind of an encoding scheme, which will say, like, if you have to compute a cell, like basically if it is a non-distinct value, denote it if the cell value will be 1, and if the particular cell value is computed previously by some smaller powers, you make it -1 and count all the non-distinct powers between that range by counting the ones. And how did we go about listing down all the non-distinct power combinations while computing a smaller power value? Is by using a simple technique of power swapping. And how did we do the technique of power swapping? By listing down the factor pairs, right? And is that all, or was there a corner case? Yes, there is a corner case if the base is a perfect power. So if the base is a perfect power, that itself can be expressed as its perfect power valuation, and then the factor power swapping can be applied with one more level deep down, and you could find new bases that will yield the same value. So this is the key idea to solve this non-distinct powers or distinct powers finding problem of Project Euler. And this technique of encoding it with 1 and -1 and then doing so, actually if you look at it, we are not even finding the value of what is 8 power 68, but only thing is we are finding out whether 8 power 68 to be computed, or if it is computed by some other smaller powers. That's what we are finding, and just putting a 1 and -1, which means this solution or this approach is going to be scalable for any range, right? You tomorrow increase it to 10 power 5, 10 power 6, 10 power 7. All that you need is a 2 by 2 grid, which can be well kept in memory, and the values will be encoded as 1 and -1 based on the logic we set. So now in the next video, we will talk a programming implementation of this idea, which is straightforward, right? So the idea is the key here. The programming implementation is direct implementation of the approach of power swapping technique, which we saw in slide number 6 and 7.